So this time we want to prove Kelvin's theorem. Let's recall what we want to do this time. We want to prove that if G is a bipartite graph, say bipartite multigraph, then its least edge chromatic number is same as its maximum degree. For that, we introduce these concepts. So what's the motivation for this concept? Let's briefly discuss the motivation first. So this F choosability is more general than just K choosability. So least chromatic number K, meaning that if we have a list assignment so that every list at certain vertex is always at least K, then we can finish the coloring. So that's what it means to be it is K choosable, or least chromatic number is K. So let's just forget the H for now. Then this F choosable is more general concept than that. We allow that for different vertices we have different list sizes. And the reason why we consider this kernel is that assume that we want to prove something like this. So assume that we want to prove that if, say, every list size at the vertex is at least as big as the degree of that vertex plus 1, then we want to say that there is the coloring. Imagine we want to prove something like this. Then one possible way of proving it is that we collect all the vertices which has a color, say C, in its list. And we actually choose some of them and color with C. Imagine that there could be a H here, and there should not be any H's here, because we want to color these vertices with the same color C. So this must be an independent set. And then once we color this, what we want to do is we want to do the induction. So we want to still finish the coloring for the remaining vertices, and we keep do that. But while you're doing that, in order to use the induction, we take this remaining vertices, remaining graph. Then we still want this to satisfy the condition. For now, because we already colored these vertices with color C, and then we wish not to use the same color anymore, so we delete C from each of these, list of each of these vertices. So these vertices get the list size decrease by 1 on, say, these vertices. In this case, for this vertex and this vertex, it's okay because originally its list size is bigger than its degree plus 1. And then for these two vertices, this list size decreased by 1. And also degree decreased by 1 because it has a neighbor in here, which are deleted. But for these two vertices, if it has no neighbors in this independent set, then for this, list size decreased by 1 because we delete C from every vertex. But but degree didn't decrease. So this approach might fail if there are some vertices in this set which doesn't have any neighbor in this stable set, in this independent set. So this gives us the idea that when we take this independent set, so we actually choose this, and then we color the vertices with the color C. We get to choose this independent set. When we choose this independent set, we want to choose so that every vertex which has a color C in its list has a neighbor here. So if we can find such an independent set, then we can make this argument work. But even with that, we are not so happy about the end result. This is not so strong statement. Because essentially, I mean, this can be proved with an easier argument. We just color with a greedy coloring. Then, greedy algorithm, every x has if you order the vertices, then it has at most, it's degree many earlier neighbors, so you can always finish the coloring. So even with this statement, we are not happy because it's not strong enough. So we want to actually lower this number. So one of the way to lower it is that instead of, considering its degree, we give some orientation. And then we just want to show that we take the out degree or in degree. It doesn't really matter, it's symmetric. But let's say we take the out degree. Then this is smaller number than degree. So if we can prove that this ensures that there is a coloring, then this is a stronger statement than this. And for this to work, here, if you go through this imagination of this argument again, then what we want is that these vertices not only have a neighbor in this set, say S, but it also have an out neighbor here. So that motivates the definition of this corner. And also this corner perfect is motivated because here what we wanted to do, we have the graph. In graph, we take some set, namely the set of vertices which has C in its list. There, we want to be able to find the independent set, such that every neighbors in this set, say U and S, in this U has an out neighbor in here. So this set of vertices with U, it's the induced subgraph. So every induced subgraph has a corner inside. So that's the situation that we want to have. Then this induction argument would go through. So that motivates this definition. So with that definition and the argument that we imagined, we can actually prove this lemma. Lemma proved by Bondi, Opana, Sigel. So if D is a corner perfect orientation, so G is a graph, and we give some orientation to make it digraph. And in that digraph, if it is corner perfect, then we say that that is the orientation that we gave is a corner perfect orientation. And let's say fx is same as its out degree plus 1 for all vertices. Then we want to prove that this G is F-choosable. By the way, this kernel perfect is, not all orientations are kernel perfect, because if you simply consider some, say, directed cycle, odd cycle, then it doesn't contain any kernel. Let's assume that this vertex is, let's assume that there is a kernel, and let's assume that by symmetry it contains this vertex. Then these two cannot be in the kernel, because kernel itself must be a stable set. And again, this alone is not kernel, so at least one more vertex must be in the kernel here. But now what happened? This vertex must be outside of the kernel, but it doesn't have any out neighbor in the kernel, in the set that we take. Because, it has an out neighbor only this, but this cannot be in the kernel, otherwise kernel is not independent set. So this is outside the kernel, but that's a contradiction that it is a kernel. So not every graph has a, not every digraph has a kernel. So now we want to prove this lemma. This lemma that for given kernel perfect orientation, and we can, find the coloring of G from its list, so that as long as the list has size at least out degree plus 1 at every vertex. So let n be the number of vertices. What we want to do is we want to use induction. We use induction on n. And basis case is okay. As n equal 1, then it's easy. So assume n is bigger than 1. And consider an arbitrary list assignment L with, at each vertex it has size f of x. So we choose a color C which appear in some list. We will do as we imagined before. Let U be all the vertices, so that its list contains this specific color C. And let S be a kernel of the induced subgraph, say induced subdigraph D, which is induced by this U. So again, what happened? We have U, and then there are vertices outside and inside, and we take a kernel S. What we do is we assign color C to all vertices in S, and which causes no problem as S is a stable set. And what we do is we delete C from list of V for each vertex V in U minus S. So for all these vertices, we delete the color C. And we further delete, say, colors from list if necessary. To reduce the size of the list for each x in, say, t prime, where let t prime be t minus u. You delete the vertices. And we want to delete the vertices, the colors from each list of the vertices, so that the number of remaining colors is exactly f prime x, where f prime x is 1 plus t, the out degree of the vertex in t prime. So meaning that this vertex could have an out neighbor here, right? Then even if this doesn't contain any color in each list, say it has a, b, a prime, then you might just want to delete one color so that we can artificially make that its new list has size exactly this much. And since every vertex in, say, u minus s has an out neighbor, in S, that's the definition of kernel, we have this f prime x is strictly smaller than f x for all vertices in u minus s. So this L prime, say we let L prime be the resulting list assignment of T prime. Then this L prime actually satisfies the hypothesis of this lemma. So by induction hypothesis, T prime is F prime choosable. So we can complete the L coloring for G by combining an L prime coloring of T prime with the with the vertices in S being colored by C. So this finishes the proof of this lemma. So we have some lemma which is stronger than just using grid coloring. I wouldn't say it's stronger than using the grid coloring, but stronger than this trivial, condition. And now what we want to do. Our original goal was to prove the H chromatic number of bipartite graph. And this shows that if we want to find the list coloring of, so here this is vertex list coloring of some graph, then we might want to find kernel perfect orientation where each vertex has not too many out degree. Then we might get that we might get the conclusion that this is some number choosable with the number not so high. So what's natural to do it next is that when we have some graph that we want to find its H chromatic number, H least chromatic number, then we consider its line graph, and then we give some orientation to that line graph, and that orientation is kernel perfect. So what we can prove is the following. Let G be a bipartite graph. Let's say XY by graph. Bipartite graph with the partition XY with multiple edges allowed. And let C be a proper edge coloring of G using integers. For an HE in the line graph of G, which corresponding to edges UV and VW in G. So these two are edges of G, but vertices in the line graph with its coloring. Say UV is colored with the number strictly smaller than VW. We orient this E from UV to VW if V is in X. And we orient it from VW to UV if V is in Y. So what it means is that we have X and Y, and this is 1, 2, 3, and this is E1, E2, E3. So these three edges. This 1, 2, 3 is this coloring C. Then in the line graph, we have E1, E2, E3, and then edges between here and here. Now we want to give a orientation of this line graph. So this E1 and E2 shares a vertex B. So this is B, which is in X. And this number and this number, the second number is bigger. So this is E1, this is E2. Because the vertex they are sharing is in X, then we direct from E1 to E2. So we give this orientation. So now we see the other two, E2 and E3. So this is E2, this is E3 because 3 is bigger than 2. But vertex they share, so sorry, this is Y. Vertex they share is in Y. So in this situation, we want to orient from bigger to smaller. So here. So we give this orientation. And let's write one more thing. If there is multiple edges in G, become pairs of, say oppositely directed edges in the orientation. Meaning is, if there is, say, E4 and D5, then no matter which one is bigger, I mean, in the coloring, we get these two both of the orientation here. So then the conclusion is this resulting orientation, say D sub C. So C defines this of this line graph is kernel perfect. So this gives us some way of finding a kernel perfect orientation of a line graph of bipartite graph. So which is what we need, right? We want to show that the bipartite graph has H chromatic number, certain H chromatic number. That's what we want to prove. For that, we want to first find the kernel perfect orientation of the line graph of the bipartite graph, and then we want to apply this lemma to that kernel perfect orientation to show that we can finish the coloring of the line graph, which transforms into the H coloring of the original graph. So let's prove this. Again, we want to use induction. Okay, before using induction, let's first note that to prove something is kernel perfect, we want to show that every induced subgraph has a kernel. But if you consider that if you consider a subgraph, say H of G, the orientation of this line graph of H that results, this always comes from the restriction of C to the edges of H. Is exactly same as the subdigraph of DC induced by the vertices, which represents the edges of H. Meaning that in here, if you take certain induced subgraph, then we exclude this vertex, E3. Then that's same as we delete this E3. Here, these two are same. So what we do is we delete some edges here, and then we go through this to produce this line graph with the orientation is same as taking induced subgraph here. So what is sufficient for us is if we just prove that DC has a kernel, since the same argument applies to each induced subdigraph of DC. because we have this G and then some C, and we get this orientation DC. And if we prove that in this case, this always has a corner, then if we consider a subgraph with a C restricted to this H, then we get another, say, DC prime, which also always has a corner. But in that case, this is actually a induced subgraph of this larger one. Not only that, every induced subgraph of this always comes from some H prime and some H coloring. I mean, and you take DC prime, then you get this. So every induced subgraph of this also comes from the same procedure. So if we just prove that for arbitrary graph G and arbitrary proper H coloring of G, if you do this, then you get a graph which always contains a corner. Then we automatically prove that every induced subgraph of this also always has a corner, so that the orientation is corner perfect. So it's enough to prove that, I mean, this graph DC always has a corner. So we want to prove that, and we use induction on the number of edges in G. And base case is trivial. When the graph has no edges, then it's trivial. Otherwise, let's call on H of G as X maximal if its color is higher than the colors of all other color sharing its endpoint. Sorry for this. I should have disconnected the internet. Give me a moment. Let me turn off my phone. Sorry. Where were I? Okay, so we define X maximal to be this. So meaning that if you have an H, say this H, and then it has an endpoint in X and an endpoint in Y, and if it has H value 3 and this is 2, 1, and let's say here we have 4. So this edge has a bigger number than any other edges sharing this vertex. But there are edges which shares the other vertex has a bigger number, but this has a bigger number than the other two. So this is X maximal. So the reason why we define this is that roughly what we want to do is we have this G And we want to use the induction. So we want to choose some E, some H, and we delete. And then by induction hypothesis, in here we have some kernel. Of course, this E has to be selected carefully in advance. Then with that choice, that we want to show that this kernel can be somehow extended to the kernel of the entire graph. And somehow we can maybe incorporate this V inside of this S. Okay, let's say this is actually line graph. In this line graph, we find this kernel, and then we add back this E, and somehow show that this S can be either the kernel of the original line graph LG, or it can be extended to. So that's roughly what we want to do. And somehow we want to choose this E well, so that this extension is possible later. Okay. So for that, we consider this set of X maximal, edges. We will see how it will be useful in this strategy later. So let X be the set of X maximal edges in G. Wait, so this doesn't make sense. Let's give other name. Let S be the set of X maximal edges. And if this S is happen to be a matching, in G, then what do we know? Then S is a stable set in the line graph of G, and is a kernel in the above orientation, because every edge outside S must shares an endpoint in X with an edge in S, and S that edge as an out neighbor in TC, meaning that if there is an edge UV, then we consider all the edges incident with U. Among that, 1, 2, 3, 4, we choose the edge with the largest, C value. Then this edge must be X maximal. So every edge, if this UV is not in S, then it has an out neighbor in S. So every edge of G outside S has an out neighbor in this orientation of line graph. So S satisfies that, and we assume that this is a matching, so it is automatically a stable set. So in that case, this is actually kernel. if this is not a matching, so in this case we are done because we already found the kernel in this DC. So in that case we are done. So it must be a not kernel. We can assume that this is not a kernel. That means this later part cannot be go wrong, so that this first part must be problematic. So it is not stable set, which means it is not a matching. If this is not a matching, then how can it be not a matching? You have x and y, and each vertex here, there is no way that we include two edges to S. Because this is C is a proper edge coloring, meaning that one of them has a larger value than other, then the other is not S maximal. So this cannot happen. The only possible thing that can happen is that this edge E1 and E2, E1 has the largest value among all the edges incident with this U1, and E2 has the largest value among all the edges incident with U2, but they share the same vertex in Y. So if that case happen, say let y, uy and wy be edges in S with a common endpoint y in capital Y. So, and we may assume that one is bigger than the other. Let's say uy is the one with the smaller c value. So we have x, y, u, w, y, 1, 2. So now this wy is our choice of deleting. So recall that in DC, so let's say this is E1, this is E2. What was the definition of DC? In DC, so this is the situation. So from bigger one to smaller one, we always orient if they share the edges in Y, we share a vertex in Y. So E2 to E1. So this is the orientation that we get in DC. So now what we do is we take this E2 and we delete. So that's our choice. So let G prime be G minus WY. Then by induction hypothesis, the orientation of LG prime obtained by deleting the vertex WY from DC. Recall that this DC is an orientation of the line graph of G. So WY is a vertex there. This has a kernel, say S prime. We have two cases. If this UI is in S prime, then this S prime is also a kernel in DC, since WY, this one vertex which is not in the smaller graph, has UI as an out neighbor in DC. So this is DC, this is original G. You delete this W y. And we take this d prime, and then we found this s prime. And this is kernel, so this is independent set. And then every vertex in d prime has an out neighbor there. And then now we put back this one vertex, which is in dc, but not in d prime. And it again has a out neighbor here if uy is in S prime. So we found the kernel. In that case, we are done. But what if uy is not in S prime? Then this is uy w. Then what do we know? Then uy must have an out neighbor. So if uy is here, not in S, then it must have an out neighbor in S prime, right? Because S prime is kernel in this induced subgraph. And ui is outside of the kernel, so it must have an out neighbor in S prime. But what do we know? Since ui is X maximal, all the edges incident with this u, all edges incident with this u has a smaller value than, let's say this is 5, then this is 3, 1. Smaller value than this uy. In that case, let's say this is E1, E2, this is E prime, E double prime. Then E prime and E double prime, in here, E prime and E double prime, they all oriented towards this E1. Which is uy. So these are not out neighbor of u. So out neighbor of u, if it exists, so here this is E1. Its out neighbor, which is in this S prime, this must share y. This must be something y. So all edges leaving it in dc minus wy go to vertices of line graph of G prime. So this, that represents edges incident to y in G prime. Hence, there must be some gy in S prime or some, say, g in X. So there must be some g here. Then, what do we know? This E1 sends edge to this gy. This ui sends an edge to gy in here, meaning that this has value bigger than 5. Sorry, wait. Which one do we say? Okay, smaller than 5. So how we choose was this. So we know that this wy has a bigger value than uy, And then this gy is a out neighbor of uy. But how we define this d sub c is that if they share the vertex in y, we orient from bigger value to smaller value. So this must have a smaller value than uy. Then this shows that the value of wy and value of uy and value of gy are ordered in this way. So also wy has this gy as an out neighbor in DC. Hence, in this case, S prime is a kernel in DC. So in any case, we found kernel. So this shows that this given orientation given by this rule, always we can find the kernel. So such an orientation is kernel perfect. So now we are ready to prove the theorem by Kelvin. So we want to prove for given bipartite graph which might have a multiple edges, its edge chromatic number is maximum degree. So let K be the maximum degree of given graph G. We know that its edge chromatic number is same as maximum degree. So we know that its edge chromatic number is K. So what we want to prove is that so what I wanted to say was that this is already we know, so we want to show that it is KH choosable. So let C be a proper KH coloring of G using colors in bracket K. So all the colors are between 1 and K. And from this edge coloring, we form the orientation DC specified in the previous lemma. So again, we have this 1, 2, 3. Then, depending on whether they share a vertex in X or Y, we orient the, edges in its line graph. So between E1 and E2, it's E2 to E1 because we send edges to the smaller part, and here E2 to E3 because if we share the vertex in X, we orient from smaller to bigger one. And now what we want to show in this orientation, we want to show that its out degree is bounded at every vertex. So in order to apply this lemma, it's better if all the vertices has low out degree. So let's bound the out degree of an edge, say xy. X is a vertex in X and Y is a vertex in capital Y. And if we have this edge whose edge coloring is I, then in this DC, the vertex xy has at most I minus 1 out neighbor. So x, y this has value I. Then out of these edges, the out neighbors which shares an edge with y, so in this LG we have this xy. It has two types of out neighbor. Out neighbor that shares something with y and that shares something with x. All of this must have a C value small. So it has at most I minus 1 out neighbors. Because this C is a proper edge coloring. All the C value here are different. And there are I minus 1 distinct numbers smaller than I. So this many out neighbors sharing the end vertex Y. So this representing edges of G with endpoint Y and at most K minus I out neighbors representing edges with endpoint X. So hence every vertex has out degree at most K minus 1 in DC. Then the previous lemma implies that this DC is corner perfect. So by applying the first lemma that we proved, so this line graph is K-choosable. So this proves the Kelvin theorem. And then now, by using this, we can also show that for non-bipartite graph, which possibly has a multiple edges, we can actually show that this holds. So we will prove it we will next prove it.